欢迎我们的战略。
很高兴有机会来这个海大很中央研究院演讲。对不起，我不会打中文，我的中文名字是赵胜。我是台大1970年毕业的。很高兴今天有机会这个演讲，在这儿演讲。这个Lakeside 醉月楼，在我的印象里，醉月湖是一个小小的水塘，在这个台大的新生大楼的河，现在是这么美丽的一个湖，尤其这个湖的名字叫醉月，让我想起李白的诗。我特别高兴，这个在这个美丽的湖边演讲。我今天要讲的题目呢，其实是我最近10几年来的工作的一种总结。我要开头是叫做 Conformal Invariance Perspective from Geometrical PDE。我要讲的东西呢是比较靠几何分析。To start with， 对不起，我很多中文不太会讲，要用英文讲，尤其是数学方面。我们大家都知道这个 Kg 就是高勋 curvature， 我们 compact surface， 两度空间一个 compact surface mg 上有一个 curvature， 叫高勋 curvature。那高勋 curvature 最重要的这个 formula 呢，就叫做 Gauss-Bonnet formula。Gauss-Bonnet formula 是说 2 pi Euler characteristic 是 2 minus 2 genus。2减2 genus is number of 4 2 pi genus Euler characteristic 是等于 integration of Gaussian curvature。那这个 formula 呢有丰富的几何和分析的含义。On the left hand side is topological information, tell you how many pores are on this surface. On the right hand side is geometry or analytic information, the integration of the Gaussian curvature. So it's a beautiful formula. And it comes out. I have to punch hard. It's fine. A consequence of a Gauss-Bonnet formula is the uniformization theorem. So you can classify the compact surface according to the sign of the Gaussian curvature. Okay. So that means if this integration of Gaussian curvature is positive, then this 2 pi Euler characteristic is positive. If you have the Euler characteristic is equal to 2 minus 2 genus, so if it's positive, then that means genus is equal to 0. So in that case, that means there's no hole on this surface, closed surface, so it's a sphere. So it's topologically a sphere. So that means if the integration of the Gaussian curvature is positive, then you already know the surface is homomorphic to the two spheres. And you can otherwise, if it's negative or 0, you can similarly classify the homomorphism type of the surface. And that's called uniformization theorem. Actually, you can not only classify according to homomorphism type, you can actually classify according to diffeomorphism type. And to see that, you need to use more analysis. So there is this equation called prescribing Gaussian curvature equation. That is, given a metric G on the surface, a measurement on the surface, you try to deform the metric by multiplying it by a positive function. To emphasize it's a positive function, I denote by e to w. And I call the new metric GW. And this kind of changing of metric is called conformal change, in the sense that you preserve the angle of two. You only stretch the length of each vector, but you always preserve the angle of two vectors. So it's a conformal Under conformal change of metric, the W and the KGW is satisfied this PDE. So the usual way to prove the uniformization theorem is to say you can solve this PDE to make, given a metric G, you can make the Gaussian curvature to become a constant under conformal change. So KGW is now become a constant, and the constant, the sign of that constant is according to integration of Gaussian curvature. The sign of the integration of the Gaussian curvature. Okay, so in this case, then we know that this integration of the Gaussian curvature is a conformal invariant. By this, I mean under change of conformal metric, this integration is the same. So this term in two surface is actually a topological invariant in two surface, but it also in particular is a conformal invariant quantity. So the goal of this lecture is try to say that this phenomena in two dimensions can it be generalized to high dimension. Okay? So the goal is to see if there is a higher order, higher uniformization theorem for manifold of higher dimension. Okay? Trying to generalize this result to high dimension. Now, of course, we only have very limited success, but let me report some success here. So the outline of the talk is first, I would recall how to generalize such result approach to uniformization theorem from four manifolds. So we will review Gauss-Bonnet integral on four manifolds. And then I would like to say that this, instead of this prescribing Gaussian curvature equation on surface, on M2 now, we have this Gaussian curvature equation. And we will see that this equation, a second order elliptic equation, now should be applied to a fully nonlinear version to see the higher order conformal invariant. So this is and then I begin to describe some geometric and topological results just from four manifolds. And then I begin to talk a little bit about n-dimensional result, very partial result. And then this n-dimensional result is this concept of conformal invariant of the highest order, nth order conformal invariant in n dimension is very related to this conformal field theory, in particular a concept called renormalized volume in high dimension. And I will briefly mention a work of a lot of other people, but without giving specific credit and specific result. And then if I have some time, I'd like to mention some compactness result on this conformal compact Einstein manifold. And this is more recent work of myself with Yang Jianping, Bo Yang, and also with Yixin Ge, which is a work in progress. So let me start with four dimensions. So the goal is trying to see if there are higher order conformal invariants, and from this higher order conformal invariants, the integral invariants, can we classify manifolds? And do we have a little bit of a result in the direction of uniformization theory? So let's recall on four manifold. On four manifold, we have this Gauss-Bonnet formula. So we do not have to know specifically what does each of these terms mean. And basically, this is a Weyl curvature, and this is scalar curvature, and then Ricci curvature. Because we are on high manifold, higher dimensional manifold, we now have curvature tensor. So the Weyl curvature usually is describe how flat is the manifold. Say on R4 or on S4, wire curvature vanishes. And this other term is usually describe how curved is the manifold. Okay. But here, the important fact we want to use is in 4 dimensions, wire curvature is a pointwise invariant. That is, if you change G to GW, wire of GW is pointwise stay the same as exponential minus 2WY. So as a consequence, this D volume form on 4 manifold is e to the 4W e to e. This EVGW in my metric is e to the 4W EDVG. So these 2 terms cancels. So as a result, this first term, wire square D volume, is the same as wire GW square with respect to this conformal metric D volume. So as a result, I'm saying that in this Gauss-Bonnet formula, the first term, the wire term, is a pointwise conformal invariant. Pointwise conformal invariant. So we have the left-hand side is a topological invariant, and the right-hand side have 2 terms, and the first term is a pointwise conformal invariant. So the consequence is the second term, this quadratic term, curvature term, integration of that is a conformal invariant. So that's the key fact I'm going to use. And now, this term is relatively difficult to study. One of the reasons is this is a minus sign. We all know that when we estimate some quantity, if it's a positive quantity, something quadratic square, it's much easier to estimate. And here we have cancellation. Something square minus some other thing square. So how do you estimate it? How do you see what's the integration? The sign is a competition of the scalar curvature with the Ricci curvature. So fortunately, that it turns out this quadratic term has a specific structure, and I'm going to explain a little bit of that structure. And it turns out on the manifold there is something called Shelton tensor. The Shelton tensor is a specific combination of Ricci to scalar curvature. And the fact we want to use is the 4 remaining, the 4 curvature tensor, RIJKL tensor, can be split into wire curvature and then some wedge product of this Shelton tensor with the metric. So from conformal geometry point of view, this first term, wire curvature, is a pointwise invariant. So all the information, how the curvature changes under conformal change of metric, is contained in Shelton tensor. Okay. And with that understanding, Jeff Wielkowski studied the Shelton tensor and studied its symmetric function, elementary symmetric function. So what does that mean? And that means the following thing. The first symmetric function of the Shelton tensor means you study the trace. Think about the tensor as an m cross n metric, and you study the sum of this eigenvalue. So it's summation lambda I, and then in this geometrical term, it turns out to be a multiple of the scalar curvature. So study the trace of the Shelton tensor, it corresponds to study the scalar curvature, and that's the tradition study of the so-called Yamabe problem. And here, we are interested to study the second symmetric function. The second symmetric function now is summation lambda I, lambda j, add up. Okay? And that turns out to be the norm of the trace square, so you think about lambda I, lambda j as summation lambda I square subtract lambda I square. So you have trace square minus this, and you write it down. So it's a multiple of scalar curvature square. Now, there's a negative sign and multiple of a Ricci square, and so on. And the unsymmetric function of this Shelton tensor is the determinant. Okay, and it turns out Now, the constant is exactly right that on 4 manifold, the second symmetric function of the Shelton tensor is the part of this Gauss-Bonnet formula, which we are interested in. So why does that help us? And that is because of the following fact. We begin to look, we know that, so what I have just said is that on 4 manifold, this integration of we call the second symmetric function, sigma 2 of the Shelton tensor is conformal invariant. And then, why is there advantage to study this integral then? Let's look at the pointwise way. What does that mean? A scalar curvature minus 3c squared. Okay? So, the advantage of studying this integral is the following. Suppose on a manifold, the scalar curvature is the averaging of VC. Okay? So if the scalar curvature is positive, and then the second symmetric function is positive, then it turns out this VC tensor, so you have two quantity which is positive, then the VC tensor is a metric, 4 by 4 metric. That become a positive definite metric. So if this 2 function is positive, you have control of this 4 by 4 metric. Every eigenvalue of it is positive. So these are interesting to study. And if a RC of a metric is positive, there are a lot of topological consequences, like the first fundamental group is finite, and the Betti number, first Betti number is 0, and so on. And then the second advantage of this symmetric form is the following. So under conformal change of the metric G to GW, the Shelton tensor changes. And the Shelton changes by changing W to hashing W. So look like hashing W, the trace of that is plus. So that's the Gaussian curvature equation. But here we study not a trace, we study the full hashing. So the hashing metric, and then plus some first order terms, dw with dw. Okay. So this is under conformal change, the Shelton tensor changes by hashing of w plus some lower order perturbation term. So to study its symmetric function, it's almost like study the hashing w, and that's similar to the four-leg and linear PDE of studying Monge-Ampere equation. So for example, the equation that if we do not we ignore the lower order term, then that's like study the symmetric function of the hashing. Okay. And on plane domain Rn, this equation, Dirichlet problem, this equation is well studied, and by a lot of people, a lot of analysts and geometers in this field. And this equation is well studied on domain Rn. So that means we can apply the technique on Rn and move it to manifold and study the integral which we are interested in. So for example, let me restrict to special dimension in 4 dimensions, and if we are studying the second symmetric function, then for hashing of u, this is just Laplace u squared minus hashing u squared. But on manifold, for the Shelton tensor, notice that we have lower order term. We have hashing w and plus some lower order term. But the leading order term is almost like this hashing, the sigma 2 of the hashing u. But we have some lower order perturbation term. Okay? And this is lower order in the sense, here we have second order to the square. And here we have second order times first order. So I think about it less than the second order square. So in some sense, this added term looks like a lower order term. So in theory, you will think that maybe the technique to study this highest order term would apply to study this second symmetric function of the hashing, of the Shelton tensor. Just you use the same technique, you know PDE, the first order term is the most important term. So you expect that to be true. but the technique, the result can be applied. But it turns out the result is a little bit more delicate. Okay? It turns out that not only the leading order term is important, but the sign of the lower order term also play a role. Okay? So the sign of this plus, Laplace W, correspond to, say, scalar curvature is positive, make it plus, otherwise the sign is negative. So it turns out the lower order term, the sign, also play a role in this subject. So to say that, let me recall the second order constant. There is something called Yamato constant. You look at the integration of the scalar curvature in all metric in the same conformal class, normalize it by volume equal to 1. That's called Yamato constant. It's a conformal invariant because it inf over all metric in the same conformal class. So this is a second order conformal invariant. And then what we want to say is, on full manifold, if you have some constraint on the second order conformal sign of the second order conformal invariant, plus some integration of the fourth order, we think about this as a fourth order Laplace W squared, so it's a fourth order the integration of that invariant, then you can, the result says, then you can deform G to GW and make this sigma 2, this Gauss-Bonnet integral part of that equal to 1. And for that reason, combined with the previous result, you know that, for example, in the same conformal class, you make Ricci positive and the first fundamental proof is final. So from this sign of these two conformal invariants, you have some topological consequence. And just a couple words about the proof. The proof of this result is the following. First, under this sign condition, these two sign condition, we try to solve the PDE with sigma 2 of under conformal change become a positive function. Okay? Try to say there exists a positive function so that you can deform the metric to this under this sign condition, the integration. This is the hard step because it's not clear how to use this sign condition to say the PDE is solvable. Okay? And the natural choice of this function f turns out to be the Weyl curvature. Weyl curvature. Okay? And that's a natural choice of the condition. And then the second part is, once you get a positive thing, then you know that in the conformal class it's already in positive cone. Then you use continuity method to deform f to a constant. And that constant is according to the sign of the integration sigma 2. So f equal to 1 in this case. So that's the outline of the proof. And it turns out this result is, one can refine the argument. And this is the result I want to talk about. So there is a sphere theorem. So on full manifold, if you already assume the Yamato constant is positive, and if this conformal invariant quantity, the integration of that, is greater than 1/4 of the Weyl square, then we conclude the manifold is diffeomorphic to the fourth sphere. So I would like to think about this. It's almost like a uniformization theorem for fourth sphere, first step in the uniformization theorem. So on two surface, if you have this is positive, then you imply this M2 is already diffeomorphic to two sphere, the standard fourth sphere. And here you have another conformal invariant quantity. The size of that tell you is fourth sphere. And this condition is equivalent because these two terms add up to be the Gauss-Bonnet formula. So 1 is greater than this means this integration is greater than this topological number, 4 pi square Euler characteristic. So under this condition, we know the manifold is already fourth sphere. And it turns out this result is also sharp in the sense that once you reach a quarter, okay, So these two Gauss-Bonnet integrons happen to match now. Then the manifold can still be diffeomorphic to force field because it's a curvature perturbation. So it can be. But if it's not, then you only have two other choices. One of them is S3 plus S1. The other is the complex projective to CP2. Okay. We can pin it down to say that's the case. And so how do you see a result like that? So I would like to think about this as almost like the first step in the uniformization theorem for force field. So how do you see a result like that? These are L2 version of some pinching result. Okay. So by that I mean the following thing. So what is a pinching? Pinching is a condition which is there are many ways to say the pinching condition. Okay. And here is one way. In work of Majoran, he did is he compared the norm of vial and the traceless receipt. E is the traceless receipt or the Einstein tensor. E equal to 0 means manifold is Einstein. So you look at the vial square plus 2 traceless receipt compared to scalar curvature. So Majoran using receipt flow has a sharp result in 4 manifold. We say that if the weak pinching is pointwisely less than 1/6, then the manifold is diffeomorphic to force field and so on. But in this case, just because of some miracles and algebraic consequence, one have the weak pinching is less than 1/6 is exactly the same as the pointwise. This second symmetric function is greater than 1/4. These two numbers just matches. So these are pointwisely the same. Weak pinching equal to 1/6 means sigma 2 equal to 1 this. So Majoran established the previous theorem, this field theorem, under this pointwise condition of weak pinching. And what our theorem says is you really do not need a pointwise condition. You only need an L2 condition. And the L2 condition, the integration is a conformal invariant, and using that fact, you can move the metric in the same conformal class to a pointwise condition, and then you can apply measurements. So that's essentially the proof. Okay. And let me say that this result also can be compared to Hamilton's result. Hamilton's result is some assumption of curvature operator being positive. Here we assume some L2 curvature condition, and these two conditions overlap and do not match. Okay? Overlap with each other. And there is also some partial result this time for n bigger than or equal to 4, but that's not shown by Bishop. Okay. And so I already described the proof. And the first part of the proof is under this conformal invariant condition, move the metric to a pointwise position, and then apply Majoran theorem. But the second part of the proof is a bit delicate, so let me describe that. So in the second part of the proof, we begin to hit the condition where this integration of sigma 2 is equal to 1/4 vial squared. So in that case, our pointwise equation, integral equation, becomes sigma 2 equal to 1/4 vial squared. And in that case, when vial vanishes, we are getting into a degenerate PDE. Yeah. So the left-hand side, they vanishes. So it's not strict elliptic PDE, it's falling and linear PDE, but a degenerate type. And to overcome that degenerate type, one needs other condition to help you, and that is if B situation happen, if the metric is always